And welcome to Tvaritam.AI. In this video, we will understand the concept behind linear regression. The core idea behind linear regression is to fit the best possible straight line through a set of data points. The goal here is to predict a continuous value. It models the relationship between an input variable x and an output variable y using a straight line. For this example, if we take one input and one output variable, we can plot the data points and the predicting line. Let's say we want to predict someone's salary based on their years of experience. If you plot this data, you'll see points scattered across a graph. Linear regression tries to draw a straight line that best represents this relationship. Now that we understand the intuition behind the algorithm, let us explore the mathematical side of the model. For simple linear regression, the equation looks very similar to the equation of a straight line. Y equals mx plus b. Here, m is the slope and it tells how much y changes when x changes, while b is the intercept, that is the value of y when x equals 0. So basically the slope controls the direction and steepness of the line, while intercept sets the starting point. Now usually we will have multiple inputs instead of just one, and this is called multiple linear regression, and the equation becomes y equals w1x1 plus w2x2 plus w3x3 and so on, and in the end we add the bias term. Here each input feature like x1, x2 or x3 has its own weight. These weights determine how important each feature is in predicting the output. For example, if you are predicting house prices, your equation might look like price equals size into weight 1 plus number of rooms into weight 2 plus location effect into weight 3 and then the bias term. So each weight tells you how strongly that feature affects the final price. A positive weight increases the output and a negative weight decreases the output. The magnitude of the weight tells you how strong that effect is, and the bias acts like a baseline value. Now that we are trying to fit a straight line, we need to find the best line that captures the relations. In case of single input variable, it is a line. For two variables, it would be a plane, and so on. We need to find the best fit line, that is the line closest to all the data points. In reality, it is not possible for a straight line to pass through every single point, so instead we try to minimize the error term. Error is simply the difference between the actual value and the predicted value. To measure this error, we use a loss function. The loss function quantifies the error between predictions and reality that guides the model to minimize this value to improve its overall performance. One of the most common loss function for linear regression is mean squared error. Here we take the difference between actual and predicted values, square it, then we sum it across all data points and then take the average. Because of the square, larger error gets penalized more heavily. Another option is mean absolute error, where we just take the absolute difference instead of squaring it. Mean squared error penalizes large mistakes more, while mean absolute error treats all errors equally. In most practical scenarios, mean squared error is preferred because it works well with optimization techniques like gradient descent, which we will discuss in the next portion of our video. Now that we understand that our model needs to minimize the loss function, let us explore how we optimize the model parameters to minimize this loss. For this, we use gradient descent. Gradient descent works in a simple loop. First, the model makes predictions. Then it computes the loss using a loss function like mean squared error or mean absolute error. After that, it calculates the gradient, which tells us the direction of steepest increase in error. Finally, we update the parameters in the opposite direction to reduce the error. Hence, there is a negative sign in the given formula. This update step is controlled by the learning rate, often denoted as alpha. The learning rate decides how big each step should be when we move towards the minimum point. If you visualize this on a graph of the loss function, we usually start from a random point. Initially, the steps can be larger. As we get closer to the minimum, the gradients become smaller and so do the steps. Eventually, we converge near the minimum error. Now, if you know how derivatives work, you might think, why don't we just directly compute the minimum using mathematics? In simple cases, we actually can by taking derivatives and setting them to 0. But in many real-world problems, especially complex models, this becomes difficult or computationally expensive, and that is why we use gradient descent as an iterative and scalable approach. Now, as you can see in this slide, we start from a random point, this blue line, and then it tries to get closer to the data points as to reduce the error as much as possible. Now for the type of gradient descent, there are mainly three types. First is the batch gradient descent. It uses the entire dataset to compute gradients. It is very stable and smooth, but it is slow when the dataset is large. Second is stochastic gradient descent, and it uses one data point at a time. Hence, it is much faster as compared to the full batch gradient descent, but very noisy and the updates can fluctuate a lot. Third one is the mini batch gradient descent. It uses small subsets of data referred to as batches, providing a balance between speed and stability. Common batch sizes are 32, 64, 128, usually in the multiples of 32, but this is not a strict rule, just a convention that we usually follow. For optimization techniques, we have the basic gradient descent that works well for linear regression because the loss surface here is convex. A convex surface means that there is only one global minimum point and we don't have to worry about getting stuck in local minima. An extension of gradient descent is gradient descent with momentum, and it is mainly useful when we are using mini batch training, where we are using different batches of data or subsets of data to compute the gradients, and they can lead to noisy gradients. So instead of relying on the current gradient, it also considers past gradients. It computes a moving average of previous gradients, and this helps smooth out noisy updates and reduces oscillations. This speeds up convergence in the right direction. There is an additional parameter called beta here, typically ranging between 0.8 and 0.99, that controls how much past gradients influence the current update. An ADAM or adaptive moment estimation is a more advanced optimizer. It combines both momentum and introduces adaptive learning rates. The key idea is that each parameter gets its own learning rate, and ADAM optimizer works very well with noisy gradients and mini batches and is widely used in deep learning. However, for simple models like linear regression, ADAM is often unnecessary. Still, it can give you good results when you are using mini batches. Now let us focus on learning rate. Learning rate controls the step size during optimization and is one of the most important hyperparameters. A good learning rate helps the model converge efficiently to the minimum. But if it is too small, training becomes very slow and it will take a lot of steps for the model to converge, or it may not reach close to the minimum point even after a lot of steps, as displayed on the graph on the top right. However, if it is too large, the model may overshoot the minimum point and fail to converge. Common learning rates are usually 0.1 or 0.01, but you can do iterative testing with a range of values such as 0.001, 0.003, and you can increase in the same manner. Or you can also start large and then use learning rate decay to make the steps smaller. Now, exploring more about learning rate decay helps improve training by taking larger steps in the beginning and smaller, more precise steps later on. Even though gradients naturally get smaller near the minimum, decay can still help in faster and more stable convergence. It is usually an optional hyperparameter. There are three common types of learning rate decay. First is the exponential decay. Here the learning rate decreases by a constant factor every epoch. Example, if gamma equals 0.95, the learning rate reduces by 5% each epoch. So learning rate of 0.1 becomes 0.095 after one epoch. This results in smooth and gradual reduction. In step decay, learning rate drops at fixed intervals. For example, it reduces by half every 10 epochs. This method is more controlled and scheduled. Adaptive decay is a performance-based decay method where learning rate reduces when validation loss stops improving. It uses parameters like patience, that is the number of epochs to wait. It is useful when training plateaus. Now for convergence criteria, it helps us decide when should we stop training our model. As we don't want our model to keep training forever, at some point we need to decide that it has learned enough. There are few common ways to do this. First is loss threshold. In this method, we stop training when the loss becomes smaller than a predefined value. For example, if we are using mean squared error and we decide that an error below 50 is acceptable, We can stop training once the loss drops below that level. This approach is useful when we have a clear error tolerance and we know what level of performance is good enough. It works well for linear regression because the loss surface is convex. However, if threshold is set too loosely, the model might stop too early and not learn properly. Iteration count is used to simply fix the number of iteration or epochs. It is the simplest approach as it guarantees predictable training time and ensures that the model will not run beyond a certain limit. But the downside is that it does not guarantee convergence and the model might stop before reaching the optimal solution if the count value is less. In practice, this is often combined with other criteria and this is used as a safety valve where we have a fixed max number of epochs that we want our model to not overshoot. Gradient threshold is another method, and here instead of monitoring the loss, we monitor the gradient. If the gradient becomes very small and goes below a certain threshold, it means the model parameters are no longer changing significantly and we are very close to the minimum. So we can stop the training process. This is especially reliable for convex problems like linear regression because a small gradient strongly indicates convergence. Last is early stopping. Early stopping is based on validation performance. Here, we train the model on training data and evaluate it on a separate validation set. And if the validation loss stops improving for a certain number of epochs, we stop training. This helps prevent overfitting where the model starts learning noise instead of useful patterns. We usually define a parameter called patience, which tells us how many epochs to wait before stopping. Now let us explore regularization. Regularization is a technique used to improve generalization by penalizing large coefficients. In machine learning, one common problem that we face is overfitting, where the model performs very well on training data but poorly on the unseen data. This happens because model starts capturing noise and regularization helps control this by adding a penalty term to our loss function. One of the commonly used regularization method is L2 regularization. Here we add the squared sum of weights to the loss function controlled by a parameter alpha. This shrinks weights towards 0 and prevents any single feature from dominating. It is stable and widely used and often the default choice for regularization in linear regression. Second is L1 regularization. Here we add the absolute sum of weights to the loss function and it can push some weights exactly to 0. This makes it useful for feature selection as it may effectively remove some irrelevant features. ElasticNet is a combination of both L1 and L2. It is useful when features are correlated and we can control how much of L1 and L2 we want to use. This gives us a balance between L2, the stability, and L1 providing the sparsity. Now one pro tip of how we can create a polynomial regression. Even though linear regression models a straight line, we can make it more powerful using feature engineering. For example, you see a linear regression fit that is a straight line. Instead of using x as our input variable, we can also include x square, x cube or something similar, and this will make the model polynomial. Here the model still is linear in terms of weights, but relationship becomes non-linear. This is called polynomial regression and it can help capture more complex patterns in the data. Thank you.